Okay, we're back to energy of activation, enzymes. This is enzyme video 2. Again, what we said was that an enzyme lowers that energy of activation, as you see here. So my chart here, I wanted to show you energy on the y-axis, reaction on this. You can see that a reaction without the enzyme has to go over that hump. But with the enzyme, it lowers that energy of activation. Takes it down the path of least resistance. So enzymes can not only catalyze a reaction going forward, it can also catalyze the same reaction going backwards in a reversible reaction. It can speed it up in both directions. Okay. Here again, substrates, active site. Now, how can it release the product? Well, here's what happens. Remember I said that when you put things together in a mixture, they stay different. They stay just like they were at first. They just associate. But when you put things together chemically, the whole thing changes. So when you make this product, all of a sudden, see, these things were being pulled in. They still had, they like a kid sitting in a chair that they didn't want to sit in. They jumping around. So these things are still trying to, because of Brownian entropic motion, jump out. But the bond is holding them in. Now, once you put these two things together, that's a whole different entity, different chemical. So now it's able to leave, and that's what I'm explaining here. If the Argus pulled them in, but when the chemical bond is formed, it changes so that now they will jump out. They didn't want to be in there in the first place. So now that it's different, there's no attachment to the active site. Now, the attachment to the active site of the substrates can never be covalent. If it's covalent, it'll bond permanently. So it's any other type of interaction, but not a covalent bond to do that. Okay. So here's kind of, this is, you can read through this here yourselves. It's what I explained already. All right. Active site, come in, form, and jump out. Again, demo. Things you can look at. All right. Now I go to cofactors and coenzymes. Okay. I go back, slide 182. I go back, in my model I mentioned, I'll start here, that however some enzymes contain sites that bind cofactors or coenzymes as needed. So I kind of put it here. It could be within the active site. It doesn't always have to be right there. But a cofactor, so we go back here. All right. Let's go back. Cofactors. Some enzymes require something additional. If they require that, no matter if you have everything that you have, they still are going to need that. That's what we call a cofactor or coenzyme. Generally, if it needs something inorganic, it's called a cofactor. And if it needs something organic, it's called a coenzyme. However, some call everything cofactors. Okay, so, but generally a cofactor is inorganic and a coenzyme is organic. Now, let's go back to earlier chemistry. We said that you had 32 elements primarily that you would work with in the human body. Among those was something called trace elements. The main role of the trace elements, the ones that all together you need a small amount, is to act as cofactors, like molybdenum and so forth. Remember vitamins. You only need a small amount, the body didn't make it. The main function of vitamins are to act as coenzymes. The main function of vitamins are to act as coenzymes. Okay? So we come with cofactors. Now in certain cases, like I said, some use cofactors for the whole thing. So here's something else you can glance at. But if you need a cofactor, i.e. coenzyme or both, then it will not work without it. That's where vitamin deficiency syndrome problems can come in. So you can read on that also. Cofactors, coenzymes. I'm not going to get very heavy into that, but you will hit it again in my course, AP1, AP2, and in nutrition too, and also in microbiology. Okay, so I'll go past that. Now I'm coming to what we call inhibitors. I'm coming now to inhibitors. And I think I'm going to start a new video for inhibitors. So I'm going to close here. Thank you.